Kari Kolari from VTT with his presentation about modeling brittle failure of ice. And I want to mention that tomorrow all day is mostly finished to numerical simulations. So that was initial idea to devote 1 day of workshop to methods of numerical simulations in relation to ice structure interaction. And today last presentation is make like small bridge to tomorrow. So please.
Okay, thank you, Alexei. At first, I'd like to thank you organizers for organizing this kind of seminar. It has been a pleasure to be here, and also I'd like to thank you for the invitation to be here. My talk is about modeling of brittle failure of ice, as shown here, but the main goal of this modeling is the ice structure interaction simulation. In this presentation, I'm going to speak shortly about ice structure interaction. In general, give you an overview what it is, and then I will go through three quite commonly used approaches in the modeling of ice. Let's start from this is a lighthouse. It's on the coast of Sweden, and I shot it 2003. There's a Peter Jochman from HSVA cleaning up a lighthouse from ice, and you can see ice drifting and crushing against the lighthouse. This I took from the top of the lighthouse. I was holding camera against the rail, so I was not shaking, but the lighthouse was. This is a small scale test about crushing. This is something you have seen already, so you can see line-like contacts over there and high pressure zones going from one spot to another. So I will stop. You might have been saturated for high pressure zones already. Yeah. But I think the physics of ice structure interaction is not well known enough. So we know that there is this line-like contact, and we also know that force and force pattern, it is changed with drift velocity, and structural stiffness, size of the structure, and ice properties, they have some effects on this phenomena. But what is going on close to the structure during interaction? This is a BTT test 1992, pushing flat indentor against the ice. And what was observed in those tests, and there are a lot of these horizontal cracks. And I want to point out that in fact these cracks, it's not just a one continuous crack. It's formed of small micro cracks. If you look carefully, there are large amount of small micro cracks. And the same thing was shown in the test of Lennart Fransson, Baltic Sea ice. He took samples showing that under crushing there are these horizontal cracks. And what is, I think, interesting and important, that these cracks don't start to initiate and propagate from the boundary. They initiate inside and then start to propagate. This was studied also in Joe project, and they even made calculations about this crack initiation. So if we think in a nutshell, what is the interaction process from the material point of view, initiation of crack, propagation, coalesce, and fragmentation, interaction of fragments, and so on, and this is going round and round. And if we then think modeling, physical modeling of failure of ice, it's three things I think are important. That we should somehow be able to model correct failure stress, but also correct failure modes. There are a number of models proposed that can predict correct failure stress, but not correct failure modes. And that I think is quite important if we discuss about physical modeling of interaction. If you fail in the failure mode, I don't think you can model interaction as well. So let's go to the modeling. See, cohesive bonds or cohesive elements are quite widely used nowadays. It's the idea is that between the elements there are bonds, elements are glued together, and then this bond breaks and we can model fragmentation of ice sheet or anything else. The good thing is that it's really simple to model. You can use it in DEM, FEM, maybe somewhere else. The idea is in the approach is that we consider tractions, surface tractions between two elements, and then we can formulate condition when the failure starts, and usually we apply traction separation law as a function of distance to model softening, so that the bond is not breaking suddenly, but it smoothly goes to zero. This video is one of our models using this approach. The idea was that we would use this approach to model crushing in 3D. Okay, in 2D it works fine, but in 3D the first question arises was, in ice it's quite important to take care about the stress state. So multi-axial stress state, then ice behaves differently than in a uniaxial stress state. So how can we model multi-axial stress state using traction separation? I couldn't figure out, and I think it cannot be done. And the second thing was that if we have many elements randomly together, how could we model anisotropic behavior? I don't know. It might be possible, but it must be really difficult. So, about using this approach to model crushing in 3D, I think the most critical thing is that you would need too many elements. You can't model crushed ice so that you model each particle that will be crushed during the interaction. It's not possible, I think, for many years at least, this computer capacity. So it doesn't work. So I personally believe that we should have some another approaches, like continuum approach. So phenomenological modeling is one of the most common approaches as well. So the idea is that we have some observations and variables, and we know that there's some connection between these two, and then we are trying to propose an equation to explain the relationship and to predict behavior. So, and this approach is usually used in plasticity theory and in damage mechanics as well. And it's usually it has been done in the continuum thermodynamics framework, which I shortly go through. So at first we introduce Helmholtz free energy with the variables we want to use, damage, plastic strain, and by derivating energy we can get force conjugates like stress, and then we need some equation to define when damage or plastic deformation will start, so yield surface or damage surface. And third one needed is some equation which we can use to describe the evolution of the damage. So these three equations are needed. I'll give an example. It's about columnar ice. So the objective was that we could model splittings in uniaxial and biaxial compression and also tensile modes for columnar ice. So what we know that it's elastically anisotropic. We know, in fact we don't know very well what are the elastic parameters for columnar ice. We have information about strength to different orientations, and based on that we can propose, I think, many different equations. This is what I did. Damage potential, you don't see it, but it's not that important in this case. And a damage surface. Now in this case I was formulating it in strain space. And after implementing it to Abacus FE software, the model showed to be able to model these modes which were supposed to. It's no surprise because you have the functions which fulfill the requirements. So it models tension and biaxial compression, and we have applied it in the modeling of ice structure interaction. And what is interesting to see that the cracking also in the model, it starts inside, not on the boundary. And this is mainly because there is friction. There is friction on the boundary layer. The pink piece, ice pushing against, there's friction, and because of friction there's shear force, and this area is under compression. So this is under compression, but here we can find tensile stress. So cracks don't want to start in the compression field. So the positive thing in phenomenological formulation is that it's quite straightforward, it's consistent, but the tough part is that to engineer like me, it's quite difficult to find functions, introduce the functions which fulfill the requirements, and in that way that the evolution of damage and the failure modes were correct. It's not an easy task to do. It's really challenging. Another fact when we're discussing about continuum approach is the fragmentation. How you could do that. That's one issue. So another approach which can be applied is kind of a micro mechanical approach or multi-scale approach. Let's consider ice specimen under compression. We know that under compression microcracking starts, and this cracking increases with increasing strain. And finally, ice fails, and it fails by splitting along the direction of compression. What we know that opening of cracks increases volume. Well, that's obvious. But what is interesting in this, that we can, in continuum sense, consider this volume increase as an inelastic strain. So if we know what is the displacement jump between crack faces and crack normal, we can formulate inelastic strain tensor by integrating over all the cracks in the volume. And then we have inelastic strain, and we can calculate stresses using the well-known formula. It's quite simple. But before we can do that, we should be able to define the crack openings. So what we should do, we should model initiation of crack, propagation, and the opening. And I've done that based on the sliding wing crack approach, which is quite commonly used in rock mechanics, studied there for 50 years. The basic idea in the wing crack mechanism is that consider inclined crack in a specimen. Under compression, the crack faces starts to slide, and because of the sliding, the wings starts to grow at the ends of the inclined crack, and wings grow and split the specimen. And the same thing happens also if there are multiple cracks. Cracks grow and finally koske and split the specimen. So how to formulate this? To start with crack initiation, I've based my formulation to grain boundary sliding proposed by Piku and Gupta. So in this case, the maximum shear is the most important component. So maximum shear direction defines where the crack will form. And I assumed that the crack size is about 65% of the grain size. That was in fact proposed by Dave some years ago. Then sliding condition. In the sliding of a crack, the friction is really important. I guess that Erland Schulson on Monday was speaking about ice-ice friction. But what is important is that the friction is highly dependent on the velocity, and it's also dependent on the temperature. So friction increases with decreasing temperature. So we can in 3D formulate a sliding condition. In fact, it's quite similar. Casciano proposed quite some years ago. And then we need some growth criteria. The growth criteria is based on K1C. It was proposed by Aspi Sammis and Hori Nemat-Nasser 1980, 1990, something. And important thing is to model interaction of these tiny cracks, and that's a challenging thing because in 3D interaction of microcracks is really hard task for an engineer. So what I've done, I've just applied ad hoc function, which is a function of average distance of cracks. It is very much similar approach as Ashby Summis had. And then the final thing is the opening of cracks. I've simply applied Castigliano's theorem based on energy release by formation of crack. So now we have everything. So I've implemented this model in the Abacus FE software as a user material model in explicit form, and here we have verification results. These are compression test results of Erland solution as a function of grain diameter, and there's compressive stress in -10 and in -50 Celsius. And here we have simulation results in red. So you can see that there's a scatter in the simulation, and that's because I've assumed that grain size is not constant. There's average grain size and then there's standard deviation. And because of this random feature, when I run for simulation, I will get different results. And it is quite similar as we can have in tests. This is a failure mode. So if ends are confined, so there's friction, then the failure mode is a bit conical shaped. When ends are free, then the model predicts pure splitting along direction of compression. Then comparison to tensile stresses, and now I have to point out that these are exactly the same material parameters. Nothing has changed. So the red ones here are simulation results. It's a function of grain size, and there's a tensile strength, and the other ones are test results. So it fits quite nicely to the test results. And just recently I've extended this model. What I showed was for granular ice, but I've extended the same idea to columnar ice. And this is example of biaxial compression. Here's the ratio of these stresses, and here's along column stress. And in this case, the red ones are test results, and blue ones are simulation results. So I would say that it quite nicely fits also to the test results of columnar ice. And using element erosion technique, I've applied this to model ice structure interaction. This is here showing the average pressure. So uniaxial compressive strength in this case is around 7 megapascals. So the average pressure is somewhere 1-2 megapascals in maximum. And it somehow predicts these high pressure zones. But I want to say that more work is needed for the fragmentation in continuum approach like this. So as a conclusion about the micromechanical model, this is a simple mechanism, but it catches quite well grain size effect and temperature effect to the strength, and also correct failure mode. And what is positive, that we don't need many material parameters, and all the material parameters have some physical meaning. So there is average crack radius, standard deviation, spacing of cracks, K1C, friction. everything which you can understand. Yeah, but the challenges are that if we think the failure modes, I'm able to model these splitting and spalling failure modes, but share-like failure, which is common under small or moderate confinement, I cannot model. So it's different failure mechanism, so it requires a different approach. And the interaction function I mentioned, that's also something which needs further work, ductile failure mechanisms, and the fragmentation I mentioned. Okay, that concludes my presentation.
Question?
Nice coverage of your model, Kari, I like it. There's a couple things. Have you looked, how do you do, I really like the grain size dependence. That's actually rare. Folks tend not to capture that, and clearly you've got that physics right there. And I like the fact that the physical basis, you've thought about that a lot. One thing, though, that comes to mind, have you looked at the rate dependence of your model?
What?
The rate dependence?
Not, yeah, I should do that, but it would be interesting.
Yeah, because that'd be another, if you get the physics right and the relaxation times and such, you might find that you have to get a little more lipstick on it to get it to handle rate dependence.
Yeah.
The other thing is, so as an empirical observation through the years in this regime that you're analyzing, modeling, the Erland's wing crack model, in the basis of that, is kind of a progressive failure. It's not a very explosive failure, but many times that's what we see in compression experiments. Mm-hmm. And so this is really more of a suggestion as you start looking at, looking at your rate effects and such. And what we see, I've actually seen this in some of Dev's freshwater indentation experiments years ago. Rather than a progressive extension of cracks as you're loading it up, and then eventually they stop, and then it breaks, and that's your peak force, your peak stress for the test. There's a sort of process where elastic deformation, all of a sudden a few cracks, and then during load up is when you actually have all your cracking occurred. They don't peak around the peak load. Your fracture rate peaks out at kind of maybe halfway there. The sample develops a fairly static looking array of microcracks that have all kind of exhausted their little pockets of strain energy, so it's more of a homogeneous stress state, but they are propagating. You don't always see wing cracks as a pervasive feature. And then that damage structure is what takes quite a bit more load until, boom, you hit the peak and everything blows apart. So I just bring that up as maybe something to think of when you start expanding that a bit. But the fact you capture the cracking away from the interface, I think that's stellar. You got the orientation of those cracks right, that's stellar. So there's a lot to be said for the way you thought about the micromechanics. So that's all good stuff.
Thank you, Dave. And I would certainly appreciate to discuss with you about the crack initiation, and that's pretty simple in this case, but
May you clarify a little bit, because you said that you count grain size. Is it by crack spacing?
Yeah.
How grain size is it?
So I assume that crack size is 65% of the grain size, and then there's a crack distance is the same as the distance of grains. So in practice there's a crack in every grain in that line.
I think that question just comment. something is familiar for me when you're talking about the cracks, propagation, and interaction between cracks, and that is something is hydrofracture problem. And over there, they are concerned with their simple model. I don't know, are they the same? Or usually they are simpler. But in some sense, there is the kind of similarity between the ice crashing model and what's happening underground. Underground, we understand even less. We cannot see what's happening there. But still, we need to find the small cracks, how they go through each other, and what they are doing. So there could be interesting parallels with that hydrofracture field.
Yeah, thank you. I will consider that.
Yeah. Very nice model. I'm a big fan of the wing crack mechanics, and in my own work, I never got to the point of looking at the coalescence. So it's a very nice treatment of that. And I guess one of the things I was curious about when I was looking at the same type of issue, I used to run into mesh dependence, and then I had to use some reference volume corrections to make sure that it became sort of mesh size independent. Have you looked at the mesh size dependence and how that influences like the size of your contact areas and those sorts of things?
I haven't done it in a simulation of ice interaction, but I've some preliminary tests done with the small scale, so that the cube I'm pressing is double sized and the elements are double sized. And at least that simple test, it don't exhibit any size dependence. And I think one reason is that there is scale inside the element, the size of the crack. So it's not like a strain softening model in that sense. So it's.
So your element size is on the order of the grain size? Is
it could be even smaller, but then there's 0.1 crack per element.
Yes,
Yeah, so it's that's
as
the
long
idea.
as it's
Yeah,
below,
yeah, that's, yeah.
below the physical
Yeah,
size, then
yeah.
fair enough.
Yeah.
Question? Again? Thank you very much. And then we finish.